Okay, the guys in the office said that they are ready. Todd said he might be a little late. He's in traffic, so I guess we can start. If you could guys introduce yourselves to the wider team.
Yeah, definitely. I can actually, yeah. Well, yeah, I'll share my screen here. So I think that should be coming through. Cool. Yeah, welcome everyone. Nice to have a big group. We're excited to share everything we've been working on. And yeah, so we're here today talking about the Subspace BlockScience collaboration, and specific focus for today is on the parameter selection analysis that we have been working on. So just a quick look at the agenda. I'm going to start out with a quick hello from our side from BlockScience. Myself, Danilo, and Shawn are on the call, and just give some intro to who we are and what we do as an organization. Then we'll give some context on the collaboration that we've been working on with Subspace the last few months. And then the bulk of the time today will be spent on the next two bullets, the intro to the Subspace cadCAD model. Shawn will be walking us through that, and then Danilo will be going through a deep dive on the parameter selection analysis that we did. And then, as Daria mentioned, should have plenty of time for Q&A at the end of the call. Cool. So yeah, just some hellos from BlockScience. I'll start. So I'm Peter. I've been project coordinator for us today, for the collaboration. And Danilo and Shawn are with me here on the call too. So I'll hand it off to them to say hello.
Yeah, hi, I'm Danilo. I'm an engineer here at BlockScience. I'm the computational science lead on this project. So I did help ideate the formalism that we did use for modeling the subspace economy, and also describe how could we frame several of the system optimization goals in terms of quantifiable KPIs. And yeah, I think that's a very short intro, and I can pass to Shawn.
Thanks, Danilo. Hey, good morning, everyone. Shawn Anderson here. I'm a data scientist on the team, and I've been primarily working to help maintain the software product that is the cadCAD model implementation that allows us to generate data for analysis. I've also been doing supplementary work on the analysis and the results, and producing documentation.
Awesome. Thanks, guys. And I will just jump back in here. Cool. Okay, now just some really quick context on BlockScience to give you an idea of what we do as an organization as well. So BlockScience is an engineering firm. Here's our mission. Our mission statement, I'll just read it through quick. So the mission of BlockScience is to bridge the digital and physical worlds through innovative and sustainable engineering. We guide the development and governance of safe, ethical, and resilient socio-technical systems, leveraging emerging technologies to solve complex problems. So basically, we're a bunch of passionate engineers interested in socio-technical systems, complex problems, and yeah, of which Subspace is included. And then this is sort of just our mission statement as a diagram or as a visual. And if we think about like technical capabilities on the y-axis, time on the x-axis, and sort of bleeding edge technology is the red line, moving up and to the right over time. And reliable technology being the blue line, also moving up and to the right, but it sort of represents more of the technology that is actually useful. And our goal at BlockScience, given our mission, is to try and close the gap between those two lines. And then just quickly, how we do that is actually with the engineering lifecycle. So this is what we practice with our clients on the projects that we work on. And so this is sort of the traditional, you may have seen this traditional like engineering, the V model from systems engineering. But at BlockScience, we also consider these three additional components, the ideation at the front, the operations and maintenance on the end, and then this loop of governance and evolution of the system. These are particularly important for socio-technical systems. So yeah, this is what we practice with projects to help them meet their goals. And now to give some context on the BlockScience Subspace collaboration. So this is a overview, timeline, and some of the artifacts we've produced while working with Subspace. So we started back in September, actually, of last year, generating the cadCAD model. So this is when we worked on the economic digital twin, economic system digital twin. And then we sort of transitioned in November to more of a economic design workflow. We were producing more documentation, research artifacts, the overall goal to sort of develop and design the issuance function for Subspace. And then around in February through April, we were working on this parameter selection analysis that we'll spend most of today talking about. And then, of course, today hosting this workshop and have been working the last few weeks on some of the documentation that we'll be walking through today. So that's the high level. And then just to sort of circle back to the engineering lifecycle, give you an idea of some of the phases of the lifecycle that were covered through this project: ideation, conceptualization, requirements and design for the issuance function, and then the implementation and integration and testing is more on the parameter selection analysis. So this is sort of where we progressed through the project. Now to look a little more detail on how we did it. So focusing on the economic design initiative, this was, as I said, focused on the Subspace issuance function. The goal here was to recommend the functional form of the mechanism, satisfying requirements and desirables related to token issuance in the Subspace protocol. This kind of looked like basically a bunch of iterations of mathematical modeling, discussions with the Subspace team, redesigning the model, making sure that all the requirements were met, all the stakeholders and incentivization was reflected appropriately in that functional form. And so yeah, this was basically produced along the way a bunch of research artifacts that are uploaded onto the GitHub repo. We'll have links for all of this stuff later, but yeah. And then just to give an idea of what that output actually was, this is slightly simplified version, but this was the functional form for the issuance function that was proposed in the end of that initiative. This top part being sort of like the main function, and then we'll be talking about the reference subsidy as well, which is sort of represented by this bottom part here. And then just to give a quick context of how we go from functional form to something that's actually implemented. So these are snapshots from Subspace resources. On the left, we have actually the hyperbolic issuance, so that issuance function that I was showing on the previous slide. We ultimately ended up making some simplifying assumptions on some of the parameter values and ended up implementing this function down here at the bottom. And then on the right-hand side is the reference subsidy component. And it's the functional form at least has this sort of this exponential decay, and implementation-wise ended up using this spline approach. So this is something that Daria produced, and yeah, just to sort of give you an idea of how to go from this functional form, the mathematical form, to what is we see on testnet basically, and what was implemented. And then finally, the parameter selection initiative that I mentioned earlier. So this was sort of like February to April timeframe. And the goal of this work stream was essentially to determine the best overall parameters for the issuance function that was previously designed, and some of the other economic system parameters, ultimately supporting in some of the decision-making ahead of mainnet launch. So these screenshots are of the analysis, I would say, of from this initiative, but a lot of work also went into sort of designing the experiments, building out developing the model, and producing the data. This is sort of like the finished product, some snapshots of that, but I'll leave these details for Danilo and Shawn to go in today. So this is, what we'll be talking about most of today. And then, yeah, just to sort of summarize the resources that we have together. So canonical resources, the GitHub repository is basically the one-stop shop, captures everything from the collaboration, the research artifacts that I mentioned from the design phase, the analysis from the parameter selection work that we did. This is all captured in the repository. Besides that, there's these two reports. So the economic design report and the parameter selection report. These both also are on the repository, so you can find them there. But these are sort of like the canonical resources for the design phase and the parameter selection phase, respectively. So, and we'll of course be able to share links and slides and everything, so we can get these resources to everyone. Yeah, so that wraps up like the context of the collaboration and at a high level sort of what was produced. Now I would be ready to pass on to Shawn to sort of yeah, to walk us through the cadCAD model and some documentation explaining a bit about what cadCAD is, what he created with this software product, and why it's useful. So yeah, Shawn, I will pass to you, and I think you'll probably grab the screen.
Mm-hmm. Yeah, cool. Thanks, Peter. Go ahead and share my screen here. Okay, so everybody should be able to see my screen. This is the README on the GitHub. I think I can get a bit of a wider view. There's some rendering issues with the CSS. I'll just stick on the main page. Okay, so this is the README on the repository. And first, I'll just give you kind of a high level of what I'm going to go through here. I'm going to jump around a little bit, and I'm not going to be able to touch all the points in the README, but that's what the README is for. Everyone can go and take a look at it at your own pace a little bit later. But what I'm going to go through today is the stock and flow diagram that is the departure point for the model. This is what the model is based off of, and I'll talk a little bit about how this works and the motivation for producing this kind of economic model for a complex system like the Subspace network. Next, I'm going to go, after that, I'll go into the cadCAD model. I'll talk about cadCAD, what that is, why we use it, what it's composed of, and the structure of the model that we implemented for Subspace. I'll skip the background because that's just background on Subspace, and I'm sure everyone on this team is very well aware of that. And I'll talk a little bit about advanced usage. I'll talk about how the model can actually be modified to run different experiments or pursue different results or analysis. And then I'm going to jump back to the beginning and take you quickly through the quick start guide to show you how you can install the repositories, install this package, run the model, and generate data, and then get that into an analysis pipeline as a departure point to run any sort of like evergreen analysis that the team would like to pursue in the future, or maybe community members would like to run their own analysis. So that's a little overview of where I'm going to go today. Let's start with the stock and flow diagram. Let's see if I can open this up. Not sure why that's not opening in a new tab, but that's okay. Maybe I can zoom in a little bit.
We can see it pretty well.
Okay.
On my screen.
Okay, so this is essentially what it comes down to when we're talking about cadCAD modeling, is we're defining the states of the system and how they change over time. So from an economic perspective, we're particularly interested in all the balances of the SSC token and how those balances change over time through the operation and the use of the Subspace system. So we start with two issuance balances, which are going to be the reward issuance and other issuance, which is essentially vesting, token allocations, different forms of vesting. But what we're particularly analyzing is the reward issuance. We did a lot of work in this research on the reward issuance function. Rewards are issued to farmers. From there, the tokens can be transferred throughout the network. They can be staked. They can be burnt through slashing. And there can be fees collected through the operation of the system as well. So what you see bounded by a box are the different states of balances that we're tracking throughout the system. In the arrows here, the thick arrows are flows. So this is a transfer of SSC tokens from one balance to another as the system operates. And what we have here, these kind of floating terms that aren't bounded by boxes, are metrics that are being tracked. And these are the SSC metrics that we're tracking, which are sort of like aggregation of balances. So we can track things like total proposer rewards that have been distributed, voter rewards distributed, total earned supply, circulating supply, remaining issuance, and user supply, which is the circulating supply plus the staking balance. Total supply would be the user supply plus the remaining issuance. And the sum of stocks, which is going to be the total supply plus the burnt balance. And that sum of stocks is always going to be equal to the max credit issuance, which is a constraint that we can apply to the model to verify that that's never broken. So this is the highest level view of the model and the motivation of why we want to build an economic system is to track the behavior, given the behavior of the system, the mechanisms of the system, and also behaviors like transfers, staking, all the actions that agents can take. We're going to observe how these states change over time and then apply metrics and ultimately feed those metrics into, we're going to map those metrics to goals so that we can see the impact of configuration parameters on goals through the PSU methodology, but we'll get to that much later. Let's talk a little bit about the model itself and what it's composed of. So what is cadCAD? Complex Adaptive Dynamics Computer-Aided Design is a Python-based modeling framework for modeling, simulating, and validating complex system designs. cadCAD defines the rules of the game and how stocks change over time. We generate what's called trajectories, which is an entire run of a simulation. So it's starting from the initial state, iterating over time steps, running the total number of time steps, which in our simulations, we generally use 3 years. We've been operating over 3-year simulations for the analysis that we've done. And the purpose of this is to generate data set. It's like a laboratory where we're collecting observations and we can perform analysis on that data to gain insights into the system. And you can see that much deeper in the methodology and the analysis sections, which Danilo is going to cover in depth. So what are the goals of the system that we're driving this whole development work? Number 1, rational economic incentives. Number 2, community incentivization. And number 3, supply and demand equilibrium. There's some model terminology here that will help you quickly get up to speed. You'll probably want to review this before doing any sort of deep dive into working with the cadCAD model. Now, this is a point I want to spend some time on. The best way to get intuition around what this all is to understand the components that make up the file structure of the whole system. And we'll go through a couple of these. So a good place to start is with types. So you can see the type definitions of the system. Here you can see the type definition for subsidy components. Here we have the subspace model state. This is really key to understand. You can see the variables that are being tracked as the system progresses over time and the units of those variables, which can be very helpful to understand what's happening. So this is a good place to spend some time and get to understand what are the variables that the system is tracking. There's different categories here, like vesting, mechanism variables, various balance stocks of balances, reward-related state variables, network-related state variables, supply-related, and then time tracking, staking, yeah, fee-related, transaction-related, and metrics. Now, in addition to the state, what's key to understand with cadCAD modeling is the parameters. How do we parameterize the system? And depending on what parameters we select, we're going to have different outcomes of trajectories. So we have some mechanism parameters like reference subsidy components and slashing function, and various implementation parameters. We have behavioral parameters, which are callable. So I call these functional parameters. We're actually parameterizing the system with functions that generate behavior. And in most cases, these are sort of normal distributions that are being sampled for things like number of transfers that are happening between agents. I think I'm a little behind on time, so I'm going to try to pick it up here and speed up. So I definitely recommend going through the files of the kind of reading these definitions of the modules. You can go through the system constants, parameters, state, logic. This is how the state evolves over time. The structure is really good to look through. This is the highest level overview into the model. And you can see here the sequence of block definitions. This is how the model progresses and how the logic is wired together. So we have time tracking, applying the reference subsidy, environmental processes, archival process, sector onboarding, issuance rewards, storage fees, compute fees, allocations or vesting, slashing, staking and unstaking, transfers, and then calculating all the metrics that we're tracking throughout the system. Okay, I want to talk a little bit about some cases for advanced usage. We'll see basic usage quickly coming up here, but if you did want to design new experiments to be run, I think these are some departure points that you might be interested in, which would be, for example, changing the initial state. Oh, I think that link is a little bit off. It was meant to be state. But there's basically two things you'll want to look at, which is the default parameters of the system and the initial state of the system might be of interest in modifying for experimentation. A couple other points here while we're in this params.py file are the governance surface, also known as controllable parameters, and then the environmental scenarios that we're going to test all those controllable parameters against. These are the mechanism parameters that the team is interested in determining for initialization. And in the case of our research, we did a search over these three parameters, which is the reference subsidy components, the reward proposer share, and the weight to fee. So we searched the Cartesian product of all possible combinations of these parameter initializations to see the outcomes on metrics and goals to inform the team towards initialization parameter selection. Now, environmental scenarios are testing different averages for environmental inputs like utilization ratio, priority fee, slash amount, staking, and then transfers between agents. So what you see here is average values. And this scenario group passes over 4 scenarios, which are high volatility, low volatility, introducing shocks into the value over at random points in time, or introducing sustained shocks, which will increase volatility for set periods of time. So for each mean value that we want to explore, we explore those 4 different types of scenario groups. Yeah, I think that's covered. So you might want to explore modifying environmental scenarios, of course, different governance surface that you can explore, modifying the default parameters, and then also investigating logic of the simulation, which can be found here in logic.py. And just a quick example here, you can see the reward function that's the issuance function that's been defined here. And this might be of interest to the team, and you could imagine potentially tweaking the reward function or some other aspect of the logic. These are examples where we are sampling distribution. So the parameter in this case is actually, for example, here we have compute weights per transaction function, and this is sampling a generator. So those generators could be modified or passed in with different mu and sigma values. Okay, so I'm a little over on time, but I think I'm doing okay. I'm going to jump up to the quick start guide and just take you through an example quickly of how this system can be ran locally, installed and ran locally. So I'm just going to follow the steps on the README here. The first thing you have to do is make sure you have Python greater than or equal to 3.6. And you're going to need one of these two options for managing a Python virtual environment, the kind of more classic Venv library with Python for managing virtual environments, or a more modern approach, which is using Python Poetry. So the first thing you're going to do is clone the repository and enter into it. So I'm in the Subspace repository here. I'm going to use Python Poetry. And so you should be able to install dependencies with the poetry install command. That's going to install all your Python dependencies. And that'll just take a few seconds. Okay, and once your dependencies are all installed, you use the command poetry shell to enter your virtual environment. You can see that I'm in the virtual environment there. You can run all the tests for the package. And I do also recommend perusing through the tests directory to get a sense of some of the constraints that are being enforced throughout the simulations, and also just a bird's eye view of what it means to access some different points of the package and run different pieces of the simulation. So we can see all tests pass. There's one warning coming from the cadCAD library. Now, if you want to run the system, this is the command python-m subspace model, and it does come with this --help command. So it's going to give us some help on all of the arguments and flags that are available. Now, when you run the system, you can select which experiment to run. You can tell the system to save data as a pickle file. You can run all experiments. You can determine the number of Monte Carlo runs that you want, the sample size per subset. You can set the number of days, which defaults to 3 years. And you can subsample the total sweeps, which means when you're combining all of your controllable parameters with all of your environmental scenarios, the size, for example, when we ran the full data set, we generated 200,000 trajectories because you get this Cartesian product of all possible controllable parameter configurations and all possible environmental scenarios. It can create a very large set. So you might need some cloud infrastructure to generate the entire set of data. But if you want to get results easier on your local machine, you use this sweep samples flag, which allows you to just take a subsample of the total sweep space. So in this case, I'm going to run 2 Monte Carlo runs and subsample 2 points in the space of configuration. I'm going to run this locally. So this is running the cadCAD model and generating a data set locally. Okay, and as you can see here, the simulation results are saved to the directory data/simulations/psu, and then the date time that the simulation was run, and it's saved as a zipped pickle file, which can be loaded into Python as a pandas data frame. And you can open up Jupyter Lab from there to initialize analysis of the data that's been generated. And we have a few links here. Here's an example of loading that data that's been run locally. So you could copy this little snippet and it's going to grab the most recent simulation data. So if we open this up locally now, it would grab that data set that we just generated. It gives you little information on the scale and size of the data set, and then has an example of doing some per trajectory analysis over the trajectories of the data set that have been run. I do want to quickly show there's a slightly different version of that notebook. Oop, I'm not sure if I opened it, but there's a slightly, you'll see it in this exploratory directory. Instead of opening local data, you can just as easily load directly from the cloud. We have full data sets that have been generated over 200,000 trajectories, and those can be loaded directly from S3. And there is an example of that in the adjacent notebook. And just quickly, I'll go through this trajectory analysis that we have here that can be used as sort of a sanity check after simulations are run. We have various charts here. So here we're sampling 6 trajectories. Each row is a single run of the simulation. So it's going to have a fixed controllable parameter set and a fixed set of environmental scenarios that it's run through. And we can see here basically the stock and flow diagram from the beginning, the various supplies, circulating supply, user supply, issued supply, sum of stocks, which is equal to max issuance, should remain constant. And we can see how those stocks change over time. We have some analysis on fee volume, block reward, and reference subsidy. So you can get rough orders of magnitudes and ideas of how fees, block rewards, and subsidies are changing throughout the course of the 3-year simulation. Here we have block utilization. So block utilization is being generated by a stochastic process. It's basically sampled from a normal distribution. But we also have these environmental scenarios with shocks. So that's what you can see with these outliers. The system will have like an average utilization, and then it'll randomly just increase the utilization in order of magnitude, say once every 4 weeks or so, to just test the system to see what happens during increased utilization. Here we can see blockchain history size, history capacity, and free space. And here we can see the buffer size, transaction volume, delta history. And here we can see the balances, farmers' balances, operator balances, nominator balances, and the staking pool balance. So this can be used to give the analyst a quick bird's eye view into whether or not the simulation is generating what's expected. And for deeper analysis, we implement the PSU methodology, which would be the next point of this. And for that, I'm going to hand it off to Danilo to pick it up from there.
Yeah, thanks, Shawn. So I'll share my screen here. And okay, we are going to move to the next section because Shawn has just shown a notebook that we did use for inspecting individual runs. But on the recommendations that we did provide, if we look at the total size of different trajectories that were generated, it was actually 200,000. And being able to analyze at this scale requires a differentiated approach. So I will start by presenting here a bit the parameter selection report that we did hand over, because one of the end outcomes of this work was really to us to be able to suggest certain parameters to be adopted by the economic mechanisms. And the goal of this analysis at scale is really to provide a procedure on which we could suggest those numbers based on this aggregate analysis. And just to make it clear here, what were the parameters that we did explore as part of the governance surface. And I think that we also have a document of the terminology. So there is a catch in here that the terminology may be a bit different from what's used on the Subspace because it has been a somewhat independent modeling effort. But we do have this document with the terminology. Peter can share on the chat afterwards that maybe will make things easier. And we did have this list of parameters. So the idea is that we have two reference subsidy components, and each component has a set of 4 parameters of interest. And for each one, we did sweep across certain values. Like, for example, the first reference subsidy, when should it start being active after the mainnet launch? So we did sweep across 0 days, 2 weeks, and 1 month. Or the max reference subsidy, like what should be the reference subsidy during the initial period? So we did sweep 1, 4, and 7 credits per block. There is also this parameter here, which is the max cumulative subsidy. So for each reference subsidy, what's the absolute maximum that this component could disperse over the network lifetime? So we did sweep 10, 30, and 50%. Beyond the reference subsidy, we also did sweep, for example, there is a parameter about the share of the reward for towards the proposer. So we did sweep 10% and 33%. And also the compute weights to fees as denominated in channel, on which we did sweep 1, 100, 1,000, and 10,000. And yeah, this is just to provide a sense of what we did test against. And as Shawn said, we did do a Cartesian product across all the possible choices here, but also there are Cartesian product over different environmental scenarios. So what the average utilization ratio or the average transactions that you have per block. And the way that on which we did get into the recommendations was really by first, we would list the system goals, like we did map 3 goals here: rational economic incentives, community incentivation, and supply and demand equilibrium. And at the same time, we did brainstorming KPIs that could be either indirect measures of succeeding on those goals. And we did map 7 here. Like one, for example, is the mean relative community supply. The idea is that for goal 2, if we want to have more success on goal 2, it is desirable to us to have more mean relative community supply. There are other ones, like, for example, CUM rewards. So CUM rewards, it's related to supply and demand equilibrium. And in a certain sense, having less cumulative supply is better because it tends to, because the more cumulative rewards, the more you dilute the token supply. So we do have, and this is another thing, because as we do measure those KPIs over time, and we see the effect over each controllable parameter over those KPIs, it's very common to you to have trade-offs that you should manage. And I think I'm going to use that as a hook to, just quickly screen share this Medium article here. It's a Medium article that describes on a high level the methodology that we use to get into recommendations. And a cornerstone of the methodology is that more often than not, you have this situation where you have a parameter, and if you select higher values of that parameter, you can have more success on a certain goal, but this can interfere with another goal. So we can think that all those controllable parameters are a set of levers that they may enforce positively or negatively each goal. And the exact choice that that manages the equilibrium is really the subject of the methodology that we have here. And yes, and with those KPIs in mind and those goals, we do have a documentation here. Actually, it's on. I'm going to share on another document, but we do map those KPIs to goals by assuming certain weights. So we compute the KPI, we see if each trajectory is performing better or worse than the median scenario on that KPI. And we also associate a direction over, like, is it having larger numbers of that KPI better or worse for being successful in the goal? So some of the KPIs, bigger numbers, tends to be better outcomes to goals, while the other numbers are the opposite. Like mean relative supply is desirable for goal 2, which is community incentivization, while the KPI 7, which is cumulative rewards, higher values is actually bad for the goal 3. So, but at the same time, you also have KPI 5, which is rewards before the first year, that we did it in as positive for goal 2. And I mean, we do have several recommendations in here. Like we do have a global point recommendation, which is really, let's assume that we are agnostic about how much we want to prioritize goals. Let's assume that each KPI has equal importance. So we do have this very general point like recommendation, but also we do provide recommendations like, let's suppose that you are concerned solely with a single goal, like you are concerned solely with goal 2, which is community incentivization. Those would be our recommendations. Or you are concerned only with rational economic incentives. Then we would have the max goal 1. And the way in which we did get into those numbers, there is a lot of work actually before getting here. But the main idea is that for what we would do is, for each controllable parameter that we test, we would look at each KPI and try to identify if larger or lower values of that controllable parameter would help or not having success on that KPI. And we did create this table here, which is really a analysis summary, and I'm going to go over the exact analysis. But the main idea is that for each controllable parameter, we could say that, for example, we did distinguish here between positive and negative correlation, in the sense that if you have a positive correlation between the controllable parameter and the KPI, it means that bigger values of that controllable parameter is going to lead to better outcomes on that KPI. If it's negative correlation, it means that bigger values of the controllable parameter, actually, smaller values of the controllable parameter is going to reinforce success on the KPI. So essentially, plus signs tells you pick bigger, larger values in order to reinforce the outcome. And negative labels tells you select smaller values in order to reinforce the outcome. We also did distinguish here because for some cases we weren't able to detect a correlation. So some of them are simply uncorrelated. There is no effect whatsoever. And while a lot of them are inconclusive. And the way that we attach a label, like whatever there is this positive or negative association, correlated and inconclusives, is really by us inspecting first, the size of the effect, like how outsized changing the control parameter is going to affect the KPI, but also analyzing any sources of bias or cross-correlation terms. And the idea here is that positive and negative, they really have an effect, while uncorrelated, we can be pretty sure that it's not going to change the outcome. And inconclusive, we can understand it as there may or may not be an effect, but even if it has effect, given the trajectory set that we did test, given the parameters that we did test, we weren't able to deem it as important compared to the ones that we didn't have association. We also did take the care here to distinguish also between effects strength. So there are the ones that are conclusive, which is when you look at the data, the effect is very obvious. I mean, it can be an order of magnitude effect. Indicative one would be minor importance in the sense that it's not going to be. Maybe one way of thinking is the following. If you have a very, very important parameter that overly dominates the data, I mean, it's going to kind of like eclipse the other parameters. As you make your decision over the most important parameters, you still have residual effects. Like you still can have. So when we mark something as indicative, is in the sense that once you take big decisions, there is still room for small decisions. It's not going to be as outsized, but it's still something that can be considered. And yeah, and also inconclusive. And we did do this table. So we did say that, for example, let's take this component parameter here, like maybe this one, the max reference subside for component 1. What would be the effect on the KPIs? And what it says us is that for KPI 1, and I can have the KPIs here so that we can follow along. So for KPI 1, which is mean relative component supply, bigger values of that parameter is going to lead to better outcomes in regards to that KPI. For KPI 2, which is farmer subside factor, and farmer subside factor is really how much we are subsidizing farmers through rewards instead of farmers being paid by fees. So the more fees, like the bigger the share of the farmer revenue that comes from fees rather than rewards, the smaller is going to be this subsidy factor. And we did think that it's desirable to us to subsidize as a minimum as possible. So this one tells us that in terms of subsidizing, let's say, reducing subsidies, larger values of that component 1, it's actually bad for that KPI. And I mean, we can follow the logic here. And what we do is, in order to us to get to that point like recommendation for the goal, is we assume that each KPI has equal weight for each goal. And by doing this assumption, we compute a utility function, like scenarios that are better than median are worth +1, and scenarios that are below the median are worth -1. And by doing so, we can, I mean, we can run some algorithms like classifiers in order to distinguish. And yeah, that's it. That's in a summary the shape of our recommendations. And in order, I think that the most critical piece of this report, maybe is how do we get up to this table indicating the effect of the parameters? And this is really the subject of this notebook here, which is Workflows PSU. And what this notebook here does is, and by the way, on this notebook, we do have some documentation here on the terminology that we adopt. So it's definitely self-contained. We do provide here an overview of the exact data pipeline, like what makes up the scenarios and how those scenarios are then aggregated into those KPIs and then, yeah. And the idea is that the basic idea behind this pipeline is for each trajectory, we have a time series for out-of-state measurements that Shawn has showed before. All those KPIs that I will show to you, they are ways of aggregating an entire time series into a single number. So when I take this KPI, for example, cumulative rewards or the mean relative supply, what I'm doing is I'm taking a simulation of, let's say, 3 years. I'm taking out-of-state measurements and I'm aggregating everything in a single number, which is mean relative supply. And I do this aggregation for all the KPIs and all the trajectories. So essentially what we do is really create a machine learning data set with 200,000 measurements. And after we have that data set, we can use machine learning techniques in order to create do the data set separation for us. To use machine learning essentially for, I mean, treating treating the parameters as features and the KPIs as the level to be predicted. And by doing so, we are creating an estimator of the causal effect. Like we are by doing so, we are estimating how much the parameters do affect the level. It's a very fascinating topic. I mean, this article here is going to enter in more detail if you guys are curious about that. But in any case, the way on which we parse the results, if I were to summarize, is really through those plots here. So the idea is we do use two machine learning algorithms, a decision tree classifier and a random forest classifier over each KPI. And the whole of those machine learning classifiers is to summarize the dataset for us. Like, so for example, for this one here, we can see here, decision tree for the rational economic incentives. So the idea is we have this label, which can be true or false. So all the measurements on which is true are scenarios that they perform better than the median, and scenarios that are false are below the median. We have the controllable parameters as features. And when we compute the feature importance, yes, what we are doing essentially is getting an estimate of what's the general importance of that controllable parameter to steer the outcome over that label. There is some art on how you interpret that, because you must always be wary of some phenomena, like if, for example, overfitting. But as a rule of thumb, one thing that you could do is when you have overfitting, usually the overfitted features, they all have the same importance, while features that are not overfitted, usually they do have an order of magnitude importance more than the others. So when we read this plot here, the first thing that jumps to mind is for this goal, clearly we have those two parameters here that are being way more important than the others. So there is a very good chance that there is a conclusive effect. For the other ones, I must be a bit more careful because you have 4 parameters that have somewhat equal importance, and also because the effect is way smaller, I must be very careful to say that there is a conclusive effect. At best, it's going to have an indicative effect. And there is also the question of what is the direction of the effect? Does larger values of that parameter reinforces or not what I'm measuring against here, this goal? And the way that we learn about the direction is really by using the decision tree plot here above. The idea is you have all those nodes here. Each node has a condition. And what happens is that every time that you apply that condition, you are separating the data set in the sense that if the condition is true, you are going to have a data set on which like when you do those maybe a better way of explain that is look at the value here. So there is a element here called value that says that for the first node says, for example, value equals 0.50 and 0.5001 and 0.499. What this value is telling us is that about half of the data have true labels, about half of the data is more successful, and another half of the data is less successful. They have false labels. The way that decision trees works is as you apply those conditions that's on the nodes, you filter the data. And the way that we go is as following. So for example, the first condition that we have, component 1 max reproducibility is less than or equal to 5.5. If that condition is true, we move to the left. If that condition is false, we move to the right. So what we do is, okay, we have all the data. 50% is above the median, 50% is below the median. Now let's apply the condition, which is what happens if we select smaller values of that max reference subsidy. If we select smaller values, we move to the left. And we can see that the white box did turn a red box. So before we had 50-50 in terms of successful scenarios, and as we filtered the data for lower values of that parameter, we have a data set in which 67% of the data is not being successful, and 32% is being successful. So you have, relatively speaking, a lower incidence of successful scenarios. And what this says us, especially given that the data set size here is very large, what it tells us is that it's more likely than not that having lower values of the component 1 max reference subsidy is going to lead us to worse outcomes to this KPI. And I mean, if we want to know about the other parameters, we can go down here to decision tree. And it's a pretty exhaustive analysis. And there is always the fact that you must be very careful when you look at the values, because if the separation is very small, usually it's overfit. So we only take into consideration when the separation is large. So for example, this one, it did start with 50 and went to 67-32. So it may pretty much be significant, but it's not uncommon to you to have separations where you go from 50-50 towards 49.9, and when that separation is small, usually this is something that can lead you to some inconclusive result. And I mean, those decision trees and random forests is really a very fast way in order to you to analyze the entire data set in a GIST. Of course, if we need more evidence, and by the way, we do have those combos of decision trees and random forests for all the goals. We also did it then for each individual KPI. So it was a pretty extensive work of parsing one by one. And if we had any doubts, we would apply more, more granular interpretations. So like, for example, this one. This one is a bit hard to hit, but on each column, we would have the controllable parameters and their different values. And on each row, we would have the KPI, the absolute KPI values. And we have both to the histograms that allows us to see the density of the data, but also linear regressions that it's also a very interesting sanity check. And yeah, I mean, by really doing this extensive analysis of looking one by one, judging whatever makes intuitive sense, and we would make it pass a judgment, whatever there is a positive or negative collusion, and whatever this association is conclusive, inconclusive, or not. And yeah, I hope that this has been helpful. I'm sure that this is going to lead to lots of questions. And yeah, I think this is maybe an opportunity to pass to Q&A. And yeah, thanks everyone for the attention.
Awesome. Yeah, thanks, Shawn and Danilo. Yeah, great walkthrough. I hope that was helpful. And we can take some questions now. We could also, we can take questions on anything. We could also go deeper into anything that Shawn or Danilo talked about. If we want to try and look closer at the charts or certain modules of the model as well, we can do that.
This was great, Peter. I know I'm going to get some echo here. So thank you very much for that. And Danilo and Shawn, that was really a great presentation. And we're looking forward to being able to share that with our community. Are you getting a lot of echo when I speak?
A bit. Yeah.
Yeah, maybe try to mute the laptop and speak to the owl instead.
Yeah, that's what I need to do. How's that better?
Much better.
Mark, sorry, I didn't see your message, but yeah, Daria has prepared some really great summaries of this in Notion, and I've shared it with Marcus and John Ming, and it kind of breaks this down into something a little simpler. I just want to recognize, though, Daria put a tremendous amount of work into this over the last 6 months, as did Nazar, and Jeremy has been involved. So we just wanted you to see this, and we wanted to have this workshop, mostly for Daria, so we could see all the different simulations that we went through. And obviously, this is going to be very technical and more involved than a lot of people on this call can absorb, probably most people, especially here in our office. But we thought it was important for you all to see just, how much thought we really put into this. We really wanted to have this novel dynamic issuance model where we can incentivize farmers when network conditions are low. We can provide a subsidy so that it still incentivizes farmers to stay on the network. And then when network activity increases, our subsidy goes down so that they're receiving enough through the block rewards at that point. But yeah, a lot of work was put into this for sure. I know I've said that a couple times now, but I want to go ahead and see if Daria has anything she'd like to say, because I know most of this was really targeted at her. So Daria, you have anything to say?
I mean, it was not mostly targeted at me because I have been following all of this project.
We might need
But
to
I
mute.
think it,
There's echoing something.
yeah, I guess it's the Todd or the owl. Yeah. So this was a lot of this, the recording and the walkthrough and the model of that is targeted towards also the financial council that will be taking the future decisions if we want to change anything about the rewards, if we think it's not performing well, towards the ecosystem and towards maybe the ambassadors and the future. This is mostly recorded for posterity, for being able to look back at it in a year after we have forgotten all of the context that we had while taking these decisions, and being able to tweak them, because as you have heard, the simulation has only run for 3 years, and it's a simulation, but then the reality may be different, and we may need to change things. And this will be our guide to be able to do so.